Hello and welcome to the first of the Year 13 Maths videos. We're going to start off with a standalone topic on proof by contradiction. The questions in this topic are a little bit weird when you see them for the first time. To be honest, you probably wouldn't come up with a solution to these questions if you were on your own. However, there are only 3 or 4 different types or variations on these questions, and once you've seen them and you've learnt the tricks from those 3 or 4 questions, then you can answer pretty much any question that the exam board might throw at you. Okay? The other downside to these questions is that they involve a lot of writing. If they do not feel painful when you're writing them out, you're not writing enough. To be honest, they're going to feel quite painful when you watch me write the answers out to these questions. So if it doesn't feel that painful when you're writing your own answers out, you're definitely not writing enough down. Right, let's have a look at the steps that we're going to need to go through for each question. 4 steps that we're going to need to go through in each question. The questions are a little bit like our work on hypothesis testing, where we came up with a hypothesis, which was our null hypothesis, which we were trying to prove was incorrect. We're going to do the same with these proof by contradiction questions. We need to come up with an assumption that is opposite to the statement that we're trying to prove. We're then going to go through some logical steps which contradict the assumption we've made. So the first thing that we do, we start up with, we come up with our assumption. We're going to call it a negation, and it's the opposite to what we're trying to prove. We're then going to do some logical steps which contradict the negation. This bit here is going to be the only bit that's going to have some maths notation in. We're going to have a lot of English, a lot of English, a lot of English, and there's going to be quite a bit of English in this step too as well. But this is the only bit where you'll see some maths notation, and then we've got quite a lot of English around it. Steps 3 and 4 are really important. These are the steps that we're going to miss out. These are the steps that are guaranteed to be worth 1 mark each on the mark scheme. So once we've come up with our contradiction to the statement we've made, we need to state really clearly what that contradiction is. Now, if that's not down on paper and it's not really clear, you're not going to get your mark. Step number 4, we have to write our conclusion. This is pretty much guaranteed going to be a repeat of the question about what we're trying to prove. If it says, prove the following, we're going to state in our conclusion, therefore the following is true, using the exact words in the question. Okay? If we don't get that down, we're not going to get our mark. We're going to have a look at a couple of examples. It becomes a little bit easier once you've seen a couple of examples, see what I'm talking through. So, example number 1. We are going to prove by contradiction that there is no greatest odd integer. So we're looking for an assumption, a negation, that is the opposite of that statement. So the opposite of there is no greatest odd integer is that there is a greatest odd integer, and let's call it n. So assumption, n is the greatest odd integer. Okay, well, we know our odd integers go up in 2s. So if we're starting with n, let's consider n plus 2. So n plus 2, I'm starting at n, an integer, and I add 2. It's also going to be an integer. I also know that if I start with an odd number and I add 2, an even number, I'm going to end up with another odd number. So n plus 2, it's an integer and it's odd, so it's an odd integer and it's bigger than n, 2 bigger than n. So n plus 2 is a bigger odd integer than n. We've got our contradiction, but we haven't stated it really clearly. So this contradicts my assumption that n is the biggest odd integer. Okay, step 3. Step number 4, we need the conclusion. Let's write conclusion. Rewrite Read the question. There is no greatest odd integer. That's what I'm going to write for my conclusion. Conclusion. There is no greatest odd integer. Okay. So we've got 4 steps. First step, we state our assumption. N is the greatest odd integer. We've got 2 logical statements. N plus 2 is an integer, n plus 2 is odd, n plus 2 is a bigger odd integer than n. We stated the contradiction very clearly. This contradicts my assumption that n is the biggest odd integer, and we stated our conclusion. There is no greatest odd integer. We finish the question and we pick up all the marks. I'm just going to pause there. Okay, let's have a look at another example. In this case, we're proving by contradiction that if n squared is even, then n must be even as well. So we're looking for an assumption that is going to help us contradict this statement. So if n squared is even, then n must be even as well. So what I'm going to say is that there is an odd value n for which n squared is even. So an opposite statement, n squared is even, n must be even. We're going to look for an odd value for n for which n squared is even. So if we can work out with an odd value of n, and we're going to get a value of n squared which is on, well, then we've got our contradiction to the statement. So we've got an opposite statement and we're going to try and contradict it. So if n is an odd value, we know that we can write it as 2n plus 1. So 2 times something's going to be even, we add 1, it's going to give us an odd value. And now we're interested in whether n squared is going to be even or odd. So let's have a look at what n squared is. So n squared is equal to 2n plus 1 all squared. Square out my brackets, expand my brackets. I've got 4m squared plus 4m plus 1. I'm going to factorise that. I could put 4 outside my brackets, but just to make things really clear, I'm going to put 2 outside my brackets, and I'm going to factorise it as follows. So I've got 2 lots of 2m squared plus 2m plus 1. Well, if I've got 2 lots of anything, then that must be even. And if I add 1, which is an odd number, then it must give me an odd value. So I've said there's an odd value of n for which n squared is even, and I've just started with my odd values, any odd value, and I've just proven that n squared is going to be odd. So I've got my contradiction. I need to state that quite clearly. So this contradicts my assumption that n squared is even. And then I'm ready for my conclusion. Reread the question. If n squared is even, then n must be even. So conclusion. If n squared is even, then n must be even. So my 4 steps. Step number 1, I've got my assumption, my negation. There is an odd value, n, for which n squared is even. It's opposite to what I'm trying to prove. I've done some logical steps, only a bit of maths really in my answer to my question. N's equal to 2n plus 1. I've gone through, I've shown that n squared is odd. This contradicts my assumption. So my assumption was there is an odd value of n for which n squared is even. Well, I've proven that they're all odd. So it contradicts my statement. I've written that down very clearly. It contradicts my assumption that n squared is even. So my conclusion, n squared is even, then n must be even as well. Finish the question.